Okay, so what did we do last time?
We sort of went over like the properties of an algorithm,
Mhm.
and we talked a little bit about um, each word and how like sometimes it's like just a matter of semantics, right?
What do you
I don't
mean?
know if we went that far. We didn't go that far, but we just talked about like the definitions and like how to apply them or how we think they're applied.
Okay, yes, that's exactly right. By the way, a matter of semantics, what do you mean by this, if you wouldn't mind
Um,
clarifying?
so when I was working on the homework,
Uh-huh.
there would be like the exercise was picking out like these terms as descriptions of the function or the procedure, but like the function could do something as simple as like doubling the number that it was given.
Okay.
And when it would ask for correctness, I assumed like I couldn't tell if like I was supposed to assume that it's correct because that's what it does, because I couldn't think of a time it would give a wrong answer, I guess. And then like I guess that sort of answers itself. But
Okay, great. So I think I understand you, and the reason I understand you is because did you email me? Was that you?
yeah,
Oh,
yeah.
okay, good. Because I brought that question that you emailed into the slides here somewhere. Okay. Was this the question that you emailed me about?
Yeah, it was that one
Okay, so
because
let's just do this. So now, normally we won't go through homework like before it's due, but this is the first day. So I'd like to go over this question, like to clarify, right? Just to make sure that we're all on the same page. Normally, you'll go through homework assignments like, yes, it's after it's due, and there will. By the way, did you guys receive an email message from Brian? Right? Did we talk about this last time? Even if we didn't, you did receive an email message from Brian like last week, right? So he has office hours, for example, today. Did you guys receive a message from Brian? There was a message, right?
I'm not
Brian?
sure.
Yeah, Brian.
Okay, Brian. Yeah, I think I did.
Yeah, okay, good. All right, so, and there's also this peer tutoring schedule that Professor Quatney sent out. So you guys should have access to that, but more on that later. Anyway, this time I want to go through one of the homework questions, just to give an idea of the flow that's involved in answering the homework questions. I mean, maybe that's not super representative, this particular question, of every homework question. Obviously it's not, but it's one of the homework questions. So you're looking at the homework assignment and you come across this question, okay? You're given some pseudocode. So here's a procedure. It's called double, whatever. And you want to check off all of these properties that this pseudocode has, right? So let's just start checking one by one. So let's say I have no idea, what is this finiteness, correctness, effectiveness? I kind of sort of heard this during the lecture maybe, but I also have my textbook next to me, right? So I open up my textbook here somewhere and I look at those definitions. They're also on the slides, these slides, which I'll post on the main page. They should be up there under files somewhere, but I'll post them on the main page so you have access to it. And I've summarized these definitions here in gray on the slide that you're looking at the moment. So let's just go through this one by one. So these are just brief summaries of those definitions that we had on the previous slide. Does the algorithm have an input?
Yes.
Does this procedure have an input, basically?
Yes.
Yes, it does have an input. So here it is. What's the input? Any positive integer is an input to this procedure, right? How about the output? Does this have an output?
No.
There is no output, right? It doesn't produce any output, this procedure. So no, there is no output. It doesn't return anything. Just as a caveat, I must let you know that we will see some examples of algorithms today that do not explicitly return a value, right? But they're still valid algorithms. So we'll talk about sorting, for example, later today. Now, if you're used to, this is an aside, but if you're used to languages like Java, for example, where you're asked to, when you write a method, you're asked to explicitly say what the return type of your method is, you'll say something like the void return type, meaning that it doesn't return anything. But you're still able to, let's say, sort an array of elements by calling a method that returns nothing. How is that done? You pass in a list. It's usually, or an array. It's usually a pointer to the first element in the array. Same thing in C, for example, if that's what you're used to. So the caller of the method passes in a memory address where that array that is to be sorted is stored. And the method chugs along, does its computation, rearranges the elements in the array. That's called sorting in place. And it doesn't have to return anything because the caller also has the pointer to the position in the memory, to the memory cell where that array is stored, where that array begins. So there's no need for the method in Java or for a function in other languages to return anything. That's called sorting in place. You mutate the array that's passed to that function. And you can write algorithms that way by using functions that do not return anything. But the details of this are of no concern to us. Like right now, let's just get back to this question. We'll look at the sorting example later today. Okay, so this guy doesn't return anything. Is this guy definite? Is the guy definite? It doesn't have the quality of definiteness. Yes, so why is that?
Because it follows like I guess a normal, or like it follows a control flow that only varies with like the input, I guess. Like it doesn't.
You can have a definite algorithm that has a control structure that does not vary, does not depend on an input. So that's not the only thing, right? So let's look up the definition. It is that you're correct. You're correct in that it is definite, but why is it? We also need an explanation. So here's a summary of what it means for a procedure to be definite, right? So what was it? So, I mean, it says here, but here's the definition here, more fuller definition here of definiteness. So each step of the, well, actually, it's almost full there, so it's not that long. So each step has to be precisely defined, right? Do I have each step? Is it clear what this step for? I only have like 3 lines. The first is just the declaration of the procedure itself. Then I have a while loop. Is it clear? Is it conform to the syntax of our pseudocode? It's clear what it does, right? While, and then you have a Boolean condition, so something inside that evaluates the true or false, like n is greater than 0. And then how about this line? Is this line clear what it does? It assigns to n twice its own value. So if n is 5, it assigns, it was 5, now it's 10. If it was 22, now it's 44, and so on. So it's clear what each line does. So definiteness simply means that each line is clear what it does. It's precisely defined. That's simply what it is, definiteness, right? If I had a syntactic error, for example, in a line, that wouldn't be definite. But in this case, we have the property of definiteness here. So this works out. How about correctness? Is this algorithm correct? Now, by the way, notice that as you remarked, by the way, in the very beginning, it's not even clear, like, what is the purpose of this pseudocode? Does it compute anything? This is actually buggy code, right? This is an infinite loop, right? So if you wrote this, your compile, well, actually not compilable, but you would run this, you would lapse into an infinite loop. You'd have to terminate with your control C somehow. So, right? Or until the stack memory runs out, it will crash on you. But it keeps running, right?
Professor, I have a question.
Yes, question, please.
Can an algorithm be correct even if it doesn't have an output?
Good question, right? So no, the answer is no. So this guy didn't have an output, and it's also incorrect, right? If it's correct, then it has an output, but not conversely. So good question, right? So this one, so this one is incorrect simply because it doesn't produce an output, and correct algorithms must produce output, right? Are we on the same page? Right.
Yeah.
Okay. So how about finiteness? Is this pseudocode finite?
No.
Okay. So why is that?
Because it's, as you said earlier.
Yeah. Yeah. So it doesn't have a finite number of steps. It is an infinite loop. So it goes on in. So it's not finite. Doesn't have the property of being finite. Okay. The next one. This may sound kind of counterintuitive at first, right? So, but is this algorithm effective? Is it effective? What does it mean for it to be effective? This may be, if we were to conduct a poll, there may be differing opinions, but let's just use the definition that we have and have the performance of this algorithm conform to that. Let me get the light while you're thinking here, so I can see. think this would be better. Okay, so is this effective?
So is that just doing what it's meant to do in a, I guess, timely manner, or like something that's useful?
Effective simply means that each step, of which I may have a finite number or possibly an infinite number, as in this case, right? Each step takes a finite amount of time. That's all effectiveness means, right? So it's kind of,
Yes.
right? So this one then happens to be effective, kind of strangely, maybe to some people counterintuitively. It is an effective algorithm, despite it's having this infinite loop. Why is that the case? Because this guy takes a finite amount of time. It just simply resets the registers, right? So it assigns to n twice its value, right? Multiplies it by 2. Okay, and then that you might know from your operating systems course is just very quick inside the computer, right? Just resetting 1 bit somewhere, a couple of bits, in fact, depending. Okay, so it's effective. How about generality? It's general. That applies here, right? According to the definition, because we know what inputs it takes, and all we require is that any input of this kind, of this form, let's say, okay, there's this vagueness in language itself. This form is accepted by this procedure. Okay, so does it take any positive integer? Yes, it can take any positive integer and do whatever it's doing. Now, infinitely many times, but yeah, so generality applies here. Okay, so that's essentially the process, right? So these terms can be confusing at first, but again, just to recap, the way we go through these homework questions is simply we'll look at these homework. So first of all, it's always read it, and when you read it, and again, I don't mean to preach about this, but read this with an idea of why is this sentence here? What's coming next? Try to predict why people wrote what they wrote and why you're being asked to read this, okay? So call it active reading, I guess. And then when you get to the homework assignments, just have this reading that you've done next to you. So you go back, right? So you already have, even if you didn't understand like 100%, like every word there, you just have an idea of where it is, where it can be found. You're mapping this out in your mind, these ideas, as well as just physically the words on the page. It's already in your imagination, simmering. And when you're solving the problems, you're ready to go to the places that you need, right, to answer the questions. All right, enough of that. Any questions? Any other questions from last time? Okay. All right, so now let's talk about a couple of problems. We want to talk about 2 kinds of problem, searching and sorting problems. Okay, so what's a searching problem? Remind me. What would be an input to a procedure that we're about to write, and we'll have a couple of versions. Maybe we'll do one of them today because we want to talk about sorting as well. So we'll do one of these. Let's do linear search and binary search also, maybe binary search next time. But what is searching in general? The problem of searching, based on your reading.
You're given like a value that you want to find in like a list.
Yeah, exactly.
Whether it be like a word, a character, or a number.
Yes, okay. So that's exactly right. So you may have a list of words, and then another word. Is that word present in this list of words, which may be some huge opus of something, some Melville's novel or something like that, huge. But is that word, for example, temple, is present in this entire novel, which may be 1,000 pages long? Or you may be given a list of integers, right? And is integer 5 present in the list of integers? That's the searching problem. Now, we'll look at 2 kinds of different problems, okay? Two different ways to search an input list. The first is called a linear search, and the other is called a binary search. And we'll look at these with an eye to compare their performance in the future, okay? And we'll define exactly what we mean by performance and what measures of assessing that performance we'll have. We'll talk about that next time. For now, let's just write down the pseudocode. So here's a linear search algorithm. You likely have already written this, something like this, in your introductory programming course. So you're given this list. The way you search linearly, what do you mean linearly? Okay, by for the presence of a particular key. So for example, here's a list 72413, and I have a key, or let's call it X, because I think that's what the book uses. Doesn't use the word key, but that's just a variable name. It's common nomenclature, but let's call it X. Is like, I don't know, it's 4. Okay, so that's some value 4. Okay, let's actually just put 4 here. Then we'll give it a name. And you want to find out whether 4 is present in the list. And of course, you'll see, well, I'm looking at the list. Yeah, I can see that 4 is there. But again, we want a procedure that can be generalized. Okay, so how do we do this? Here's pseudocode on this very page. Now, I'll be asking for your help to translate this. Well, here's a description of the algorithm, but I will be asking for your help to translate this into pseudocode. Okay, so is it clear what the page says? Right? Is it clear what the page says? Okay, so here's the way we're going to do this. We're going to take a look. We have our key. Here it is. We have our array. I'm going to take a look at the first entry in the array, compare my key, which is this guy, with the first entry. Is it equal to that first entry? Yes, then okay, just return that position 1 at which this entry is found. If it's not, then continue searching. Okay, in this case, I compare 4 to 7. It's not equal to 7, so I continue looking. I look at the second entry in the array. It happens to be 2. Is 2 equal to 4? No, so I continue searching. Then I hit this one, 4. I check again, is 4 equal to 4? In this case, it happens to equal 4. It happens to equal 4. And I know I'm keeping track of the index at which I happen to be comparing the key with the value. So I keep track of these indices. So presumably there's going to be either a for loop or a while loop inside my pseudocode in a second here. And once I found this match, once I've determined that 4 equals 4, I return that 3. You return that 3 to the caller. Return 3 to the caller. If, on the other hand, I was looking for a value that isn't present in the array, for example, something like 8, then I would have to look at every entry, right? At every entry, finally determine that the entry isn't there. My index, I would have overstepped this array, right? And without having found the value. And then I would have to return, once I've determined that the value isn't there, I've exhausted the search, I've looked at every element of the array, exhausted the search. I would have to return some sentinel value indicating to the caller that the value 8 is not present in the array. So I return some value like 0. Okay, so let's write this piece of it. I think this is clear to people, right? Okay, so before we write this down, did everyone sign into Canvas? Is everyone who's here, did people sign in? Because I want to end the sign-in check-in process here. Okay, so that's that. So let's just write down this linear search algorithm. I think it's clear how it works. So let's follow our rules. We have this procedure, and let's call this linear search or lean search so that I don't have to type too much. Now, this procedure is going to have an input. What's going to be an input? Okay, so A1, A2, A sub n is going to be integers. These are, this is an array of integers. And what else? Key.
X integer.
Yeah, X, okay. X is an integer. Okay, so that's my input. Now I'm inside so what does the procedure do? Well, let's do it for loop or while loop. Let's do a while loop. I think that's what the book does. So you start with I equals 1, right? And then you look at every element inside the array. So I have a while loop, while I is not edged over the right edge of the array. Ah, that was a mouthful. Why I is less than or equal than n. So I started 1 and I look at everything until I've exhausted my search, meaning that I've looked at every element of the array, possibly fewer, because inside the while loop, my condition would be well, actually, let me use again and so that I don't get complaints like, is it like 1 ampersand, 2 ampersands? People use the different languages, right? So we'll stick with the pseudocode. We'll simply, without much ado, write and. And that's the ampersand that people have fallen in love with and while working in their favorite languages, right? So just simply and, like in Python. And I haven't found the match, okay? So x is not equal the a sub I. This is going to be my while condition. Okay, what's the Boolean inside my, just before we go forward? When will I exit this while loop? When am I going to exit this while loop? That is when, yes, please.
When I find the value that we're looking for.
But yes, or, so I have noticed that, just not to allude to your logic, but I have two conditions here. Let's call them P, like, I don't know. This is, you can ignore if this, what I will say in the next like 1 minute doesn't make sense or anything, but it should make sense to all of you almost, right? If you've taken previously. So I have a condition, so inside my while, my P and by Q must be true as long as my while loop operates. When do I exit my while loop? Whenever P and Q is not true, right? When that Boolean evaluates to false, that is P and Q is false. When does that happen? And you might remember something called De Morgan's laws, but it's not important to just remember those laws and remember the name that they're called. But you proved something in one of your logic courses, something like this. All this says is that I exit my while loop when either I is greater than n or I found the hit. That's what I was asking, I guess. When is the while loop violated? You have an end condition inside. Okay, you exit that while loop when either you've overstepped, your I is too big, bigger than n or bigger, actually strictly bigger than n, or your key hasn't been hit, right? Now, why do we have these conditions? Okay, this is something maybe if you're writing code, this comes with trial and error, right? So, okay, but let's check. So first I want to find that hit. So I keep incrementing my I gets incremented here. I, instead of some of you write I++, that's fine, but I'm going to write it this way. I gets next value of I. And two things can happen. First of all, when I exited this while loop, my I is somewhere within the range of the indices of the array. What does that mean? So I is less than or equal than n. If I exited this while loop when I was less than or equal than n, then I found the hit, right? Just think about this for a moment and tell me if you agree. So I'm going to say that if, well, in fact, if I less than or equal than n, then I found the hit. It's the only way to exit this loop, right? When I is in that range. I could have a separate variable. That may be the way the book has it, but we'll do it. We'll just simply return I, because that's the location where it's found. I think the book has a separate variable called location, which it returns, but you can just simply return I, no problem. Otherwise, else, you return something else. Else, if this didn't happen, if I is not less than or equal than n, then you've exited your while loop without having found a match, right? Do people agree? Yes, okay. So in this case, let's just return some sentinel value, like -1 would do, but in this case 0 would do, because we're counting we're accounting for our elements beginning from 1 up to n elements. Indices range from 1 to n, not from 0 to n-1. So just simply return 0. This would do for us. This is our linear search algorithm, right? This is linear search. Okay, so now let's, first of all, is it clear how this works, right? Would this example suffice, or should that we gave before writing down the pseudocode, does that make sense, or should we do another example?
So the if and else are outside the while statement, right?
Sorry, one more time.
The if and else are outside the while statement, right?
If and else are outside. So the only thing inside the while statement, right? Does that make sense? The only thing inside the while statement is incrementing I, nothing else.
Okay, that makes sense.
Right? It makes sense, right?
Mm-hmm.
Okay. Okay, so this is our, well, actually this pseudocode is somewhere in the next slide. So let me just, okay, well, maybe it's not. But anyway, this is the pseudocode for linear search. I'll post these slides later. Now, let me ask you, so why bother with this stuff? Okay, variety of reasons. One is that we want to have a stack of procedures, of algorithms, that we'll later look at and evaluate in terms of their efficiency. So next big topic is the efficiency, the so-called big O runtime of these algorithms. So we'd like to have a stock of a few representative algorithms that we can evaluate later. Now, what do we mean by evaluate? This is kind of looking ahead. Evaluate, well, assess its efficiency. Well, what do we mean by this? Well, how much effort does it take to do this computation, to find the hit, the match of the key? Well, okay, then you say, okay, I kind of sort of vaguely get, well, how much effort? Yes, I mean, if I had a larger array of elements to search, the effort will be larger, and I would completely agree with you. There are also other conditions when the effort needed to find the hit varies. We somehow need to have a quantitative measure of this, and we can begin by simply accounting for the number of operations that need to be carried out in order to find the match. Okay, then you can ask, well, what number of operations? What do you mean by the number of operations? And then I'll say, well, okay, good point, and should have been clearer. Okay, how about the number of? I could have talked about number of like arithmetic operations, but we're not really carrying out too many arithmetic operations. We have some kind of increment here. Okay, so that wouldn't be that interesting. I would say to you, how about the number of comparisons needed? So let's look at the efficiency of this, so-called efficiency, in terms of the number of comparisons that we're making, that we have to carry out in order to find a match within the array. How many comparisons am I making? And how would you quantify this? How many comparisons does it take?
N comparisons.
Okay, always.
And then if the number doesn't exist, wouldn't you not consider that x not equal to a sub I?
Yes, whenever x is not equal to any of the x sub I for any I.
Yeah, so yes. If the number doesn't exist in the list, then you don't check that at all.
Check what at all, please?
Check the x, check if I is already equal to n or greater, you wouldn't check you wouldn't check if x is equal to.
There are no more a sub i's then to even check against that x, right? You're correct. Yeah. But the remarks are correct. All of the remarks. However, what I'm asking here is, how many comparisons am I making? Let's say, again, this may sound like a trick question. It really isn't. It may sound like a trick question because you can say, well, I don't know. I mean, what is the array? You just give me an array, give me a key, and I'll count for you exactly the number of comparisons needed. That you can retort, and you would be completely right. So let's just take a concrete example, because later we'll want to abstract away from concrete examples. But for now, how many comparisons would it make if my list was like 7, 3, I don't know, 12, and I was looking for my key. So this is my list. And my key is 7. How many comparisons am I making? I'm looking for the number 7. I want to know whether the number 7 is present in the list. Do I make n comparisons? Even if I have more than 3, let's say you have 30 elements, but 7 is sitting at the front.
You have 2, right?
Yeah, I just made, exactly. So I'm just making, let's call it 1. Well, why should we call it 1? You're correct. Actually, we can account exactly how many comparisons we're making. We're making this check so this assignment we do not count. Right? We said so we're just looking in terms of comparisons. Here we have to make a comparison. Is 1 less than or equal than 3? So that's one comparison. We also, because this is an AND condition, we have to check for this. Is x equal to AI? So that's the second comparison. I actually made 2 comparisons already. Okay. So I exit the while loop because this is violated. It's not true that x is not equal s sub I, because x is equal to s sub I. So I made these 2 comparisons. I exited the while loop, right? And then I'm making this comparison. So it's really 3 comparisons, and then returning. So we're not counting for return. So I made 3 comparisons there, right inside. When I found the match at the first time around. So how about if I was looking for the number 3 in the list? How many comparisons did I make?
6.
Sorry?
Six. Six.
Oh, is it 6? Are you sure? How about I'll let you count?
Yeah,
You're
no.
close, but
5.
yes, okay. That's
5.
correct.
Could you
Anyway,
explain why?
yes.
5?
Sorry?
Could you? How was it 5? Like how do you explain it?
Okay. So do I count? Do I make this? Okay. So we will return to this later. But okay, let's do it. Do I make this comparison the first time when I'm comparing 3 to when I is 1? Do I make this comparison?
Yes.
Do I make this comparison? That's
No.
two comparison. What do you mean no?
Hmm?
Inside the while loop.
Well, I was thinking no, because of x does not equal. That's why I was thinking it was not.
No, but it's a comparison. Whether it's equal or not, you're want to determine whether x equaling a sub I is true or false. To determine whether it equals or
Okay.
not equal, you just make the comparison to get the answer, right? Make sense?
Yeah.
Yeah. So you have two comparisons. Then when I is 2, you still have two comparisons. That's 4. Correct? Then you have one last comparison before returning. Does that make sense?
Yeah.
Yeah, we'll return to this problem actually later. So if you think about it, this will make sense completely. But the point I'm trying to make here is that the number of comparisons depends actually where this element key is inside the array. Suppose now that the key is not inside the array. Then how many comparisons do I have to make? All right, let's see if people are present. Do people have video? There are some people with no videos. Oh my God, that's
It would make 2n plus 1.
yes, a good point. So, but it not good. It's a completely correct point. So please turn on your videos on a side note. So yes, so you'll have to look at every element in the array, right? You have to look at every single element. That's the worst case. The best case, you find it at the very start. That's excellent. You don't have to exert too much effort now with this procedure to determine whether you've hit the key or not. But if the key isn't there, you have to look at every element, right? At every element inside the array. That's what we'll later call the worst case scenario. Worst case scenario in the sense where it's worst in the sense that you have to perform the highest number of comparisons in order to run this procedure. And we'll be interested in the worst case running times of our algorithms as we proceed in the next section. So we'll return to this. But for now, with these ideas in mind, here's our first pseudocode of linear search. Let me tell you a couple of words about, binary search, and we're not done with binary search. We'll return to it. Binary search serves exactly the same problem as linear search. It's just a searching problem. Determine whether a key is present in the array. However, the binary search is much more efficient, and it does not work for all kinds of inputs. It requires its input array to be sorted to begin with. So binary sort cannot work with this array. So I can call linear sort, I can call linear sort lens, oh, I'm sorry, did I say sort? Why did I say sort? I mean search, linear search and binary search. We're talking about search. So I can call linear search and pass these two arguments, right? The array itself and the key. But with binary search, and we'll write it next time, binary search, its output will be exactly the same as with linear search, but its input must be sorted. So it will only take the array that's sorted for it to be able to run, okay? And well, the key, same thing, the key here, okay? It could be looking for another key. As we'll see, well, when we write down the pseudocode for binary search, and we'll probably do it either later today or next time, we'll also assess the number of its efficiency in terms of the number of comparisons that algorithm makes. And it will turn out that the number of comparisons there is much lower than in the case of linear search. And we will be a little bit more exact with these claims. We'll actually do very precise accounting of the number of comparisons made. But again, this binary search solves exactly the same kind of problem. The only difference is that it requires its input array to be sorted already for it to be able to run. Okay, so we'll talk about binary search. Maybe not today. Okay, so let's Okay, I'll return to binary search. Now let me ask you about sorting a little bit. So what is the sorting problem? Okay, so if there's something in the chat, I might have missed it because is there anything people would like to bring up? Right? So you can just let me know if it doesn't relate directly to the material separately. But are there any questions about this so far? Okay. Okay, so what does it mean to sort something? What do we mean by a sorting problem? So at the top of this page, you see the definition of sorting, right? You're given a sequence of elements, A1, A2, A3. Okay, so here's the sequence. And you're permuting the sequence of the elements. Okay, so here's A1, A2, A3, some sequence, small example here. Always when you see a definition like this, beginning to think, oh, this is too abstract. Why don't they just give me an example like that? Don't fall into these kinds of simplifications. Apply the effort to understand this in an abstract way and come up with your own example. It will stick much better with you, and you will understand it much better if you yourself apply the effort of inventing an example to fit this abstract definition, rather than rely on reading an example in the book. Do it first. Whether you come up with it or don't come up with it, you don't beat yourself up about this. If you don't, so what? You've applied the effort, you've grown. Then go on and read their example. So here's what this definition means. You're given an input. It's A1, A2, A3. What are these prime A1? What is A1 prime? Apparently that's the output. What does this definition say here? Well, you give an input A1, A2, A3, and you have an output A1 prime, A2 prime, A3 prime. As a set, the A1 prime, A2 prime, A3 prime is identical to the set A1, A2, A3. It's just the same elements, just thrown in a bag, both of them. It's just I've permuted them. I've looked at them in a different order. But the order of these primed ones is such that they come in ascending order. So here one comes before 2, and 2 comes before 3. Okay, so what we have here is that A1 prime is one of those elements. A1, it's either A1, A2, or A3. In this case, it happens to be exactly the same as A1. So what? What is A2 prime? A2 prime is one of those elements. It's either A1, A2, or A3. Well, it happens to be A3 in this example. What is A3 prime? A3 prime is one of those elements. It's either A1, A2, or A3. It happens to be A2 in this example. Well, does this definition make sense now? A little bit with a small example, right? So when you see an abstract definition, always apply an effort to invent your own example for this. And of course, you read the author's example as well, and just try to make the sense out of it. And the thing that you always do is resist the temptation to get frustrated with just having to read this definition. If you're frustrated, you feel that you're frustrated when reading the text, just leave it aside. Usually just go play basketball or something, come back to it and do it later, or walk around. Walking is great. Okay, so I don't know. Let's go on. Now we'll talk about two algorithms, sorting algorithms today. One is called selection sort, and the other is called insertion sort. They both attain the same goal, achieve the same goal. They both solve this problem here. They both solve this problem here. Okay, but they do it differently, and we'd like to look at both of them. And these are just two of many, many. Okay, so let's start with selection sort. And first, let me tell you how it works, and then we'll do a little demo. So here's how selection sort works. You're given this input. Let's say, I don't know, here's an input. Here's an example of selection sort. By the way, we have pseudocode here instead of me writing it down, although I intended to write it down. So what? Here's the way it works. You start at this first element, and then you scan the entire array, right? So you look for everything here to the right of the first element. So you fix your eye here and you look at everything to its right. While you're scanning, you're looking for the smallest, you're keeping an account of what the values of those elements are that you're scanning, and you pick the smallest of those. So in this case, for example, the smallest happens to be 2. So what you do is you place this 2 in place of 7, and you take that 7 and place it in place of 2. So now at this stage, if you've done that, your array has just become 2, 7 here, and nothing else has changed, right? These guys, 10, 5, 3, 8, 4, 9, and 6 are still there, wherever they were. Okay, but 2 is this green marker here. Signifies that this is already sorted. I've actually found the smallest element and placed it in position 1. Then you move over, you start here at this 10 right there. And then you look at everything to the right of 10. Find the smallest element to the right of 10. Okay, what is the smallest element? Well, it happens to be 3. So you interchange 10 and 3. So you end up with 2, 3, and then 5, 10, 8, 4, 7, 9, 6. Notice that stuff in purple is already sorted, right? So the 2 smallest elements have already made it to the left of the array. Later, when we'll be concerned about proving correctness of algorithms, and you will be concerned about this issue not only in this class, but also in follow-up classes like algorithms classes, analysis of algorithms classes, you will talk about the notion of an invariant of an algorithm. Now, I know I haven't defined it, but an invariant is basically something that does not change throughout the run of an algorithm. So it stays fixed. So for example, here, the invariant will be the following. Everything to the left of my pointer I is sorted. Okay, everything that's purple here, okay, let's make sure the 7 is not purple. Everything that's purple is already sorted. That's an invariant. If I ran the next iteration of this for loop here in my pseudocode, then I would get something like 2, 3, 4, okay? And then I would have the next would be 10, 8, 5, 7, 9, 6. The purple piece will still be sorted. So that would be the invariant of my algorithm, right? Now, of course, you're beginning to get an idea of what selection sort is about, but it's not super duper clear. Am I correct? But are you beginning to get the idea of what this is like, right? So basically, find the smallest element, put it in its correct position, the leftmost position of the array. Then look at the tail of the array from the second element down to n. Find the smallest there, put it in the second position. Now my tail has just shrunk. I start my tail at 3 all the way down to n. Find the smallest there in that tail from 3 to n. Find that smallest, put it in the third position, and so on and so forth. Just to make this clear and drive this idea home, let's take a look at the demo of selection sort. Okay, so here's your selection sort. And by the way, that's on the left. You see pseudocode here. On the right, you see the Java version. It's just as short. Obviously, you don't have to know it if you just the pseudocode is here. So here's the way it works. This is the array that you want to sort. 7, 10, 5, 3, 8, and so on and so forth. Okay, you start with your pointers. This is the tail now. Initially, as you begin your algorithm, your tail is the entire array. Here's the pointer I. Notice what's happening. I found the smallest element, which is at 2. I switch it with the position and I. And what's interesting is that everything to the left of I is already in final order. That will be my invariant. That I will never be worried about what's to the left of I. I will always know that it will be sorted. Everything to the left of I will always be sorted. Find min again, exchange it with the element at position I, move I upward. Everything to the left of I is sorted. Find the smallest again, switch it with I, move I up. Do people see what's happening? I will later be asking you how many, well, what's the effort exerted in sorting this array? Well, then you ask me, well, what do you mean by the effort exerted? I don't know, how do you account for it? Well, can you account for it, I'll say, in terms of the number of swaps made, for example? Then you'll say, okay, now you're being more concrete. Now I can actually think about something that you're asking. Okay, I can count the number of swaps. That would be a legitimate question, but that's to come later. That's a bit of foreshadowing for the next slide. I is pointing at 10. Where's the smallest element in the tail of the array? Well, it's sitting right there. That 5 is sitting at min. You switch min with I, move I upward, and so on. Do people get the idea? Switch, move upward. The grayed out portion is the one that's the invariant, that it's already sorted. Okay. Notice that I have to scan the entire array from left to right, beginning at I. Okay, now notice now what's happening here. The smallest element is at position I. You switch that 9 at position I, which happens to be the element at position min as well. You switch 9 with itself. Okay, the way we have that Java code up there, it does actually that switch. You can write your code to avoid that switch, but this one, the way it's written, it switches it. This one switches 10 with itself. Now you've exhausted the entire array, you're done. Selection sort is done. This is the end. Now I know that this array is in final order. Does selection sort make sense to people, right? Now, this is just one of the algorithms. The other one that I'd like to talk about is called insertion sort. So insertion sort, in fact, is an algorithm that you're already familiar with also. And you've done this if you've ever played cards, for example, certain card games. For example, if you've played, I don't know, like in bridge, for example, you want your cards to be sorted. So first of all, you group them by suit, and then within each suit, you want these guys sorted because it's easier to play that way. Okay, so it matters. In other card games, in poker, it's not that important, depending on the variant of poker that you're playing. There's no sorting involved. You group them differently depending on the game. But in certain card games, you do. The way you sort them, and here you may have done this, you receive, let's say, 2 cards. Let's say you have 2 and 4. Now the next card comes in. Let's suppose the next card that comes in is a 3. So you take that 3 and insert it in the correct position between 2 and 4. Insertion sort. If an ace came in, for example, and you were playing a game where ace counted as 1, okay, then you would place that ace to the left of 2. Again, inserting that ace in the correct position. And now you would have 1, 2, 4. If a 7 came in and you only held 2 and 4, then 7 would go to the right of 4. So now you have 2, 4, and 7, right? So basically, every time this new thing comes in, you look at what you have in your hand and insert it in the correct position of what you already have in your hand. Insertion sort. Notice how different this is from selection sort, where you selected the smallest element in the tail of the array. Once you've selected it, you just swapped 2 elements. Again, selected the smallest, swap 2 elements. Selection sort. Insertion sort, insert in the correct position. Now we have a little example here, but if this verbal description is clear, we'll run first a demo, and then we'll write the pseudocode, right? Or run this using a pseudocode. So first of all, is this clear what we've just described? Okay, let's see if people are there. I see some people. Can you please turn your webcams on, and so on and so forth, right? So please turn your webcams on if you can. Again, I don't see you all at the same time, but now let's take a look, okay? So here's the same array that we want to sort. Okay. Okay. Start this at I. Now the grayed out portion is something that we haven't yet seen, okay? So what do? Now you look, so by the way, the invariant will be, again, to the left of I, everything will be sorted. But the thing is, next, we're going to look at 10 and insert 10 in its correct position. When you start at I equals 1, well, everything at I and to its left is already sorted. You have 7, 1 element. Oh, great, it's already sorted. So you leave that alone. You move up, that's already sorted in ascending order. So you move up to the next element. So I have my 2 pointers here, J and I, looking at the second element, eyeing it. And now this J will start moving downward. And now we'll start comparing 10 with 7. So now 10 is larger than 7. So these 2 cards are already in ascending order. So in this particular case, there are no changes that need to be made to the array to the left of I. So that's already in ascending order. Now, if this 10 were something like 6, we would have to move 6 up to the front of 7, but 10 is larger than 7, so we'll leave it alone. Now comes a 5 at the next step. Now 5 is not larger than 10, so what we need to do here is notice what will be happening. We'll need to move 10 up, we will need to move 7 up, and we will need to move that 5 down. That's what will be happening. So notice there's a lot of copying going around in the pseudocode. We'll see as we run this on an example with the pseudocode. So it comes all the way down, this thing, this 5. And now this is in ascending order, right? Does that make sense? We come up to the next element, 3. Where does 3 go? Again, all the way to the left. Notice how much shuffling we need to do. We need to do a lot of copying. 10 has to be copied into the position of 3. So as looking ahead at the pseudocode, I better save away this 3. Save away. What does that mean? I can just simply say save, but save away this, stash away, let's call it. Stash away this 3 so that I can move this 10 to the position of 3, 7 to the position where 10 was previously held, and 5 to that position where 7 was stored. And now I go ahead and move that 3 up to where 5 was stored. So 3 goes there. So the next element is going to be, so 3 goes all the way down there. So now this is in ascending order. Does that make sense? And the reason I'm going through this in a detailed manner is because I will be asking later, what's the effort involved in solving this in terms of the number of maybe shuffles, shuffles, not shuffle, the number of exchanges made, for example, is compared with selection sort. Okay, well, please keep that in mind because those questions are to come up. Okay, again, where does 8 go? Just 1 down. So notice that sometimes I have to move the element all the way down in insertion sort, and sometimes not at all, sometimes halfway down. So for example, the next element 4 comes almost all the way down, right? We'll end up next to 3. Okay, so almost all of the elements. This 2 comes all the way down, right? It comes all the way down. This 9, however, just comes 1 position down and that's it. Okay, so the effort depends on the order in which the elements come in. So, okay, now this is already in ascending order. How about this 6? Where does 6 go? This time 6 goes, well,
Right in the middle.
Right in the middle, exactly. So it comes midway down. So not all the way, not right away, but in the middle. Okay, but anyway, at the end of the day, we're done. So now this is sorted. That was insertion sort. So notice how the effort needed to insertion sort an array depends on the initial ordering of the elements. Okay. Okay, so the homework assignment will ask you more questions about this. But when do you, so let me just as a preview real quick. When do you think more exchanges are needed here? When the array, okay, what should the array look like so that insertion sort has to do A, the most amount of work, and B, the least amount of work?
I think most amount would be sorted from, or okay, I guess like it'd be sorted from 10 to 2, like the opposite way.
The opposite, yeah, because it has to, because each element has to come all the way down, right? All right, that's exactly right. How about if it's already sorted? So so somebody gives you an array to sort, and that array already happens to be sorted, but you don't know, neither of you know. Just give it to insertion sort algorithm and let it sort. And the output is exactly what the input was, because it didn't have to sort anything. Then how much effort does that require? What do you have to do to run insertion sort in that case? Each time through the loop, and I know we haven't looked at the pseudocode, and we will in a second.
You'd still have to compare, right?
Sorry, one more time?
Would you still do you'd still do comparisons, right? Because you don't know it's sorted.
Yes, you do comparisons, but then, yes, this is true. So you have to look at it. So you have, I know I haven't shown you the pseudocode, we'll do in a second, but you do have to look at every element and then look at comparisons. But do you have to, I don't know why I keep using the word shuffle it down. It's not really shuffle it. Let's say sync it down to the leftmost end of the array, that element. Do you have to do too many?
Just one comparison.
Sorry, one more time?
Just one.
Yeah, just one. So you don't have to like bring this element all the way down each time, as opposed to when your array, input array, if it was reverse sorted, then you have to do a lot of work. So notice how the work needed to insertion sort an array depends on the input. If the input is almost already sorted, barely does any work more than linear work. We'll maybe not clear right now what I mean by linear work. It will be clear next week, but it's not too much work. But if it's reverse sorted, then there is a lot of work. We'll call that quadratic work later. And now it may not be clear why it's quadratic work, but it will be next week. Okay. All right. So, okay, we could talk about this for a while. Now let's look at, by the way, if you think that it's very frequent in practice to have to sort an array that's almost already sorted. For example, if you work for a bank, let's say, I don't know how many people, do you guys know what like a check is? Right?
Yeah.
People use checks like before. So these checks have numbers. So you have a checking account and you can write checks, like you could buy stuff in the store 20 years ago with checks. So those checks have these numbers, right? And when the bank is processing these checks, those checks come in almost in sorted order. So the bank might need to sort these checks that it receives, millions and millions of transactions maybe daily, but they tend to come in almost sorted order, right? Because first of all, your checkbook has these checks sorted, so you just issue them in that order. So it's not infrequent to have to encounter a sorting problem in the real world when you have to sort something that's almost already sorted. The reason I'm mentioning this is that in those cases, insertion sort, although we'll later discover that this is not the most efficient algorithm to sort things, there are much better ones. There's merge sort that's theoretically the best. And there are neat algorithms like quick sort and heap sort that are much better than all of them. Despite this, sometimes insertion sort, despite it's not being the most optimal and the quickest and the most efficient, it has its place in practical applications. Okay, so that's all I wanted to mention. Now let's move on to the more concrete stuff. Now let's get back to, so here's this. So I'll let you do, so what I've just demoed, right? What I've demoed is this pseudocode. Now the book gives you a slightly different pseudocode. It's very, very similar. So you have at the very end of these slides, you have this exercise, right? So let's do that. You're comparing two ways of writing down insertion sort. This one happens to be in pseudocode, but in any programming language, you can do it like with slight variations. It's still the same algorithm. It's just the question is, by the way, I think your homework assignment uses one of these versions and the book, the text itself uses the other one. So you have to be familiar with sort of both. Okay, the exercise version may be even slightly different than either one of these, but they're all the same algorithm. So here's what we'll do. The first one here, so this one is what I just showed. And this one is the one I think that's given in the book. So let's just run this one that's in the book and see what the differences are, right? So let's just do this exercise. This exercise, by the way, is asking you to write in your own words a one-paragraph explanation of what's going on. What are the differences? So let's take, and is this too much, too long? There's 6 elements. It's not too bad. So let's start with this one, 5. So we'll start with 5, 2, 4, 6, 1, 3. That's going to be your input. And of course, we know that the output is going to be this 1, 2, 3, 4, 5, 6, right? So we know if like these happen to be correct, there's pseudocode, and we know what the output will be. Now the job is, and this is similar to what you might see on the quiz, for example, like you might be given some pseudocode, not this, maybe something similar, and you're asked to write down at each value of I or J, whatever it's will happen to be, what's the internal state of your memory, of your machine? Like, what are the values of the variables? So let's start. Let's look at this, okay? And first of all, you start by, maybe we should make a little table, but let's start with J. We do start with J equals 2. I guess we'll make a little table. When J equals 2, and then J equals 3, and so on. And we'll fill these as we go along. So J equals 2, it will go all the way up to 6. Okay, so by the way, if you're inclined to nitpick, like I sometimes may be in asking you questions, right, for a good cause, you might say, well, J is 2, well, now then the input must be, yes, you're correct. The input must have at least 2 elements, the way this is written. So yes. So the input has at least 2 elements. So it's not explicitly written down, but that's true. So let's start with j equals 2. We remove this j equals 3. We'll get back to it. So j equals 2, what's happening then? Okay. First, you set I to 1, right? And then you have a while loop. And then you have a while loop. Okay, so help me out. We're tracing, we want to write down what's the value of a, what's a sub j right now? Where's a sub j?
2.
Yes, a sub j is this. What is a sub I? Where is it? I.
5.
I, exactly. So what does the while loop tell me to do? Is a sub j greater than a sub I? Then do something. In this case, is it? So I'm making that, keep a mental note. I'm making this comparison. A sub j is not greater than a sub I. Do I increment do I do anything with I?
No.
No, okay? So I is 1, okay? What is this all about? M gets a sub j, what's that? So what is M? Okay, so now I have an M here. Maybe I should use the same color, I don't know. We'll see later. What is M? M gets, and what do I need? What's the purpose? So I'll be asking you, what's the purpose of having this M? First, let's just follow through. So M is what? M gets what? Whatever is a sub j, right? And a sub j is 2. Sorry, one more time?
2.
2, yeah, exactly. So M is 2. So notice this corresponds to my declaration there during the run that we're stashing something away. M is what we're stashing the value of a sub j away in M. And now we'll be doing something inside the next for loop that's about to come. So what does that for loop tell me? Okay, again, this is slightly different pseudocode than below this, but it does exactly the same thing. The demo applies to either one. Sorry, one more time?
Those exchanges.
Yes, those exchanges, but let's follow through very carefully with this for loop here. So k gets set to 0. And then you're reading this, you're at the homework assignment, you're looking at something like this and you're getting frustrated, let's say, if you're in a, you're not always in the best mood every day, right? So what on earth does that mean? That's what we need to grok, right? So let's see. J is 2 right now. I is 1 right now. Okay, let's forget about M. We'll stash away a sub 2. So this element 2 is copied into M. In M, this is 2. M is 2. What is a sub j minus k? And what's the purpose of this for loop is what I want to ask you. So k is 0 when this for loop starts. Okay, so I have a 0 here, k is 0. What is j minus I minus 1 right now?
That would be the, and I guess that'd be 0 or?
Yeah, it happens to be 0. Okay, so is k running from 0 to 0? Okay, so then you say, okay, k is 0. Then I go inside the for loop. At this point, it may be just seeming weird to you, like what exactly am I doing here? But then just follow through. So what is a sub j minus k is? What is a sub j minus k? This is going to be 2 minus 0. So that's a sub 2, right? At this position. So what does a sub 2 get? Where a sub, here's what, yeah, sorry, one more time. This is a sub j minus, yeah, it was 2, but now I'm copying something into that position where 2 was. What am I copying there? What's a sub j minus k minus 1? What is that?
5.
Yes, because j minus k minus 1 is 1.
A sub 1.
Yes, right? So j was 2, k 0, minus 1, minus 9. So 2 minus 0 minus 1 is the subscript here. A sub 2 minus 0 minus 1 is a sub 1, which is 5. So what happens here is that 5 overwrites a sub j k minus 1. So 5 over, so the entry here, the list itself that I'm sorting is going to be, well, first of all, I'm not touching anything to the right of this. So 4, 6, 1, 3, those are still the same. but I've just overwritten my a sub j at 2. I've overwritten it with a 5. I have that 2 now stashed away inside M from this position. So I go ahead and assign to a sub I assign M. What is I? I is 1. A sub 1, this is going to be 2. So notice the effect of that for loop is to place 2 right before 5. So now that piece in green on my list is already sorted. Let's do one more. Now what's happening when J, so that's the list. Now J is 3. So again, start I is 1. Now this time I'm going to have I1 and then I may, okay, let's see how does I change in this case. When I is 1, is a sub j greater than a sub I? So what's a sub I? What's a sub j?
A sub I is 2.
A sub I is 2. That's exactly right.
A sub j is 4.
Okay, that's absolutely correct. So here's my new list. So here's my a sub j now. And you start with a sub I here, right? Is that what you said? Right?
Yeah.
Okay, so what's happening inside the while loop? We got 2 minutes left. We just need this iteration and it will be clear.
The I gets +1.
The I gets incremented, does it? That's the question. 4 is smaller than 5. So is a sub j greater than a sub I?
A sub I is 2 right now. It's
Oh,
not
yeah,
five.
I'm sorry. That's my
So
fault. A sub I is 2. So
So,
yes,
yeah.
so it's greater. So I increment I. So now a sub I next, and the next position gets to be a 5. Now what's happening? So I is 2. So we should write this down. So now I is 2. So this is inside, this is happening inside the while loop when I increment these i's. So I is 2. I stash away the M. Do I stash away the M? What's M?
Is J is 4.
Yeah, a sub j is 4. So M gets 4. M gets 4 in this position. Then what's happening? Now we're inside the for loop. What's going on inside the for loop? Again, this is the new. K is now 0 again. So K is 0. J was 3. So a sub j minus k is a sub 3.
Again 0.
So a sub 3 gets what? What does this, I guess my question is, what is this assignment? A sub 3, it changes to?
A sub 2.
A sub 2, right?
Mhm.
A sub 2, exactly. That's the copying over. So I guess we can call this like overwrite. Overwrite. It's overwriting. Okay, it's that way. Okay, we'll write it that way. Overwrite. Okay, so then what's happening? K now, where, by the way, okay, where does K range? K, what's J minus I minus 1?
0.
J minus, no. To begin with, right now, yes, it is. But when we began, J minus I minus 1 was what? 3 minus 1 was 1. So K ranged from 0 to 1. So I'll be doing 2 overwrites. You're correct. This is the second overwrite now. Does that make sense?
Yeah.
We should go through this. So right now, what we have is 5 and 2. Now, 4 we have stashed away. 6, 1, and 3 I haven't touched. 4 is stashed away. This 4 is stashed away into M. So when I get down to here, A sub
2.
gets, so where does 4 go?
A sub 2.
A sub 2, yes, I'm sorry. So A sub 2 goes to 4, exactly. So I have the update here is that this goes, okay, you get the idea. So now Where's my undo? So you get the idea. 4 goes here and 2 goes here. And now it's sorted, right? This green piece. All right. Does that make sense? You should run through the rest of it to make sure, because sometimes like I used a different example in a different section, and the question came up where this for loop didn't range anywhere. So this k happened to be 0, and this right-hand side happened to be a negative number. So that for loop ranged nowhere. So there was no overriding being done inside. When that happens, that means that there's no swap required.
It's already
Yeah.
sorted.
Yes. So the point is that you should run this through for different inputs. Anyway, we're done. We're a couple of minutes over. Any questions? I have another section. Otherwise, I'd stay over.
I have a quick question.
Yes.
Go ahead.
Yeah, all right. It's just quick because you were referring about there was no overwritten. So where do you find the case where it becomes overwritten?
Well, in those cases, we were overriding them. What do you? So in this case, in the cases that we've seen, we were overriding them. So, for example, when we got to 2, 5, what do we have before? So here's where we started with. We started with 5, 2, 4, and others. And when we ended up with 2, 5, 4, and others, how did we get here? We got here by saving away 4 in M, then overriding this 2 by a 5. That's how this 5 ended up here. That was the overriding that I meant. Right?
Okay, I see. Yeah.
Right. And that actually this 2 first was saved away into M. So 5 overwrote the 2. And then whatever I had in M went into this position 1, on the first step, I mean. So just exchanging the first 2 elements. So that was the overriding happened when I overrode this 2 with a 5. But luckily I had 2 stashed away, so it came into the first position to end up with this. Does that make sense? It will make sense when you go through it. Like, it's obviously you have to go through this on your own in your quiet room when no one's around, just when you're by yourself, and then it will make sense.
Yeah. Thank you.
Okay. All right. So anyone else?
Professor, I have a
Yeah.
question.
Yes, please.
The only assignments due this week is
Yeah.
the 18 questions on the website.
Yes.
That's it, right?
Yeah, that's the only one, because we had
Okay.
problems transferring this, like one of those 10-pointer assignments.
Because
that-
a couple days ago, it
Yeah.
was one more thing. And
I know.
Yeah,
I know.
yeah,
Yeah.
okay.
So yeah, it's whatever you see on Canvas is the one. We couldn't link that assignment for whatever
Okay.
reason, and I'm
Okay.
still waiting for their tech support to see why that happens. And now it's becoming too late. So for now, the assignment that you have is just those 18 questions. Yes.
Okay, thank you.
Okay. Anyone else?
Could you put this?
Slides? Yes, I will put them. Yeah.
Okay, thank you very much.
Okay. Anyone else?
Hi, Professor.
Yeah.
I have some problem about the linear binary the function. Can you scroll up? And yeah.
The binary
Yeah.
function?
Yes. The linear binary.
What do you mean? So we didn't.
I have different ideas because I don't think.
I'd be very happy to discuss the ideas with you. There's nothing I love more, but I have a class in like a few minutes.
Okay.
Right now at 3:30. So can you email me what that
Yes,
was?
yes,
And maybe we can meet over
Because-
or next time you can bring it up, because we will discuss it next time. I didn't really discuss it this time.
Okay, because I don't think I'm not sure. Like I think you did that wrong.
Yeah, it's possible. I actually
Because I tried multiple times and I tried to read by myself,
Uh-huh.
and I think it doesn't make sense at the
Okay.
beginning.
That's
Okay.
good. There's nothing
I'm
I
sure,
love more than making mistakes. Although some people
I think I was
misinterpret this.
wrong, so yeah.
Yeah. So that's a very good thing to make mistakes, because that's how we discuss and we learn. It's possible, although I doubt it. I think it's correct, but we can discuss it next time, right?
Okay, thank you. And
Right.
about the tendency, because
Oh, yeah.
so actually we need to sign in every time, like
Yeah.
before we come into class.
Yes.
Yeah, because I have one event.
Okay. So how about you email me, because I really have to go to the
Okay,
next
no
class, right?
problem. Sorry about that.
So, yeah, that's okay. Just email me and I'll address it like either later today, very late, or tomorrow.
Okay.
Okay, I'll get back.
Do you know what's the office hours
Yeah, I'll post the office hours. So right now I don't know what they're going to be, but I'll post the office hours.
Okay.
You guys got also
All
an
right.
email for Brian. For now, please see Brian or email me if you need to see me, and later I'll post the office hours, right? Okay. All right. So it was good seeing you, and I'll see you guys on Friday, and then you have the recitation, and you might hear from me via an email. Maybe I'll post a mock quiz for you before the next quiz. Just no points, just for you to just practice. Okay, so I'll see you guys on Friday. Okay, so now I'll go. So see you.